Have you ever wondered what makes up everything around you? What is at the core of everything we see, touch, and feel? Imagine a world too tiny to see, yet so immense in its impact that it literally shapes our reality. This is the world of atoms. Atoms, those microscopic particles, are the building blocks of matter. Yes, they're in the air we breathe, the food we eat, the stars we gaze at in the night sky, and even in the device you're using right now to watch this video. They are everywhere, in everything, yet they remain largely unseen, hidden from our daily view. These tiny particles, each a world unto itself, are the fundamental units of our universe. They are the silent architects of life itself, and their mysteries have fascinated scientists for centuries. In the next few minutes, you will unravel the mystery of these tiny particles that make up our universe. To comprehend the universe, we start by understanding its smallest unit, the atom. Now imagine the atom as a miniature solar system. At its heart, there's a dense central core called the nucleus. The nucleus holds two types of particles, protons, which carry a positive charge, and neutrons, which carry no charge at all. Protons and neutrons are snugly packed together in the nucleus, creating the bulk of an atom's mass. Despite its tiny size, the nucleus is incredibly dense. If we could somehow enlarge an atom to the size of a football stadium, the nucleus would be about the size of a pea, right there at the center of the field. Now let's turn our attention to the electron. This particle carries a negative charge and is significantly lighter than both protons and neutrons. Electrons inhabit regions around the nucleus known as electron shells or energy levels. Think of these shells as orbits, similar to how planets orbit around the sun. The fascinating part is electrons are never at rest. They're always zipping around within these shells at incredible speeds, and while they're on the move, they create a cloud-like formation around the nucleus. This electron cloud accounts for the volume of the atom, making it seem much larger than it actually is. The charges of these particles are what keep the atom balanced. The positive charge of the protons is exactly balanced by the negative charge of the electrons, resulting in an overall neutral charge for the atom. Neutrons, being neutral, don't affect the charge but contribute to the mass of the atom, adding stability. So the atom, a tiny universe in itself, is composed of protons, neutrons, and electrons, each playing a crucial role. These components, though minuscule, are the building blocks of everything we see around us. They are the silent players in the grand theater of the universe, dictating the rules of chemistry and physics, and hence, life as we know it. At the heart of an atom lies its nucleus, a dense central core. This minuscule heart of the atom is a bustling metropolis of particles, with protons and neutrons playing the leading roles. Protons, positively charged particles, form the crux of the atom's identity, determining the element it belongs to. Neutrons, on the other hand, are neutral particles that don't carry any charge, but play a vital role in the atom's stability. Now let's imagine these particles for a moment. They're incredibly tiny, yet they're jam-packed together in an area even tinier. You'd think they'd repel each other, wouldn't you? After all, like charges repel. But here's where the plot thickens. There's a force at play, stronger than this repulsion, that holds these particles together. It's aptly named the strong nuclear force. This force acts like an invisible glue, binding the protons and neutrons together in a tight embrace. This strong nuclear force is quite the character. It's about 100 times stronger than the electromagnetic force, which is why it can overcome the repulsion between the protons. But here's the catch. It only works over very short distances, about the size of the atomic nucleus. If a proton or a neutron strays too far, it's out of the strong force's reach. Now, you might be wondering, what's the big deal about this force? Well, its implications are huge. It's this force that makes atomic nuclei stable, allowing atoms to exist. It's also responsible for the energy produced in the sun and other stars, because it's this force that powers nuclear fusion and fission. This bustling metropolis, the nucleus, is where most of the atom's mass resides. Yet it's just a tiny fraction of the atom's size. The atom is largely empty space, with its electrons whizzing around the nucleus at a considerable distance. It's like a solar system in miniature, with the nucleus as the sun and the electrons as the planets. The nucleus, a hub of activity, is where most of the atom's mass resides, yet it's a fraction of the atom's size. Surrounding the nucleus like a cloud is the electron shell, defining the atom's boundary. This electron shell, also known as the electron cloud, is a fascinating aspect of the atom, and it's far from being as simple as it sounds. Imagine a cloud of buzzing bees, each bee representing an electron. They're not just aimlessly flying around, they're moving in distinct paths or orbitals around the nucleus. These electrons carry a negative charge and are constantly in motion, creating a cloud-like appearance. But what's even more intriguing is that these electrons don't just exist anywhere in this cloud. They exist in specific energy levels or shells. Think of it like an apartment building. The ground floor is the lowest energy level. The first floor above is the next energy level, and so on. Each energy level can only accommodate a certain number of electrons, and once it's full, the electrons move up to the next level, just like people moving to higher floors when the lower ones are filled. A vital role of these electrons is in the formation of bonds. When atoms come together to form molecules, it's the electrons in their outermost energy levels, or valence electrons, that interact. They can be shared, transferred, or pooled to form different types of bonds, leading to the creation of virtually every substance known to us. Moreover, the arrangement of electrons in an atom determines its chemical properties. This is why elements in the same group of the periodic table, having the same number of valence electrons, share similar characteristics. The electron cloud is more than just a boundary. It's a dynamic, bustling hub of activity that dictates how an atom will behave, who it will bond with, and what it will become. It's a vital part of the atom's identity. The electron cloud, with its energy levels and orbiting electrons, is key to the diversity of matter we see around us. So, we have journeyed from the heart of the atom to its boundaries, unveiling its secrets. Picture this: an atom, the most basic unit of matter, just like the foundation of a skyscraper or the roots of an ancient tree, is what constructs everything tangible around us. It's a small world, but it holds the secret to the grandeur of the universe. At the heart of the atom is the nucleus, a dense core that contains two types of particles: protons, which carry a positive charge, and neutrons, which, true to their name, are neutral. These particles are bound together by the strong nuclear force, one of the four fundamental forces of nature. It's what keeps the protons from repelling each other due to their like charges. Then, there's the electron cloud, a region that surrounds the nucleus. It's home to electrons, tiny particles with a negative electric charge that balance out the positive charge of the protons. This cloud isn't a fixed structure. Instead, it's a probability cloud showing where the electrons are likely to be at any given moment. Now, why is this important? What roles do these parts play? Well, the protons and electrons define an atom's identity. The number of protons determines which element the atom is, while the number of electrons influences its chemical behavior, its ability to form bonds with other atoms, and ultimately, the creation of molecules, the building blocks of life. And the neutrons? They play a crucial role in the stability of the nucleus. Too many or too few, and the atom could become a radioactive isotope, releasing energy as it seeks a more stable state. We've covered a lot of ground, but remember, this is just the tip of the atomic iceberg. There's so much more to explore, from quantum mechanics to nuclear fusion, the processes that power the sun and the stars. Now you have a greater understanding of the tiny particles that construct our universe. The atom. The atom, though minute, is immensely powerful. It's the fundamental building block of everything we see, touch, and experience. The understanding of atoms has unlocked a myriad of possibilities in science and technology. Nowadays, we can manipulate atoms to create new materials with properties that defy our classical understanding of physics. We're even using atoms to store and process information in the emerging field of quantum computing. Moreover, the study of atoms has also led us to the discovery of new, strange realms of reality. Quantum mechanics, the theory that describes the behavior of atoms, has revealed a universe that is much stranger and more fascinating than anything we could have imagined. It's a world where particles can be in multiple places at once, where they can tunnel through walls, and where their properties are entangled across vast distances. So next time you look around, remember, you're seeing a world constructed of countless atoms, each with its own tiny universe inside.